So welcome once again to another great video. In this one, we are on the topic of electromagnetism, and we are mostly focusing on just doing a few past paper problems. Right, so in this particular problem, we have a common test from 2022 KZN. Right, so one thing you will notice is that if you go to the question paper itself, my diagram is rotated. I just did this to save space. There's no other significant reason for that. It doesn't compromise the integrity of the question or anything, still the same thing. All right, so now here we have, well, we are told that this diagram shows a bar magnet that is dropped vertically downwards, right? So this diagram is actually like that. So the magnet is dropped like that, vertically downwards. Okay, so now into a stationary coil. Right, so even if we look at it rotated like this, it doesn't really change anything. And then the direction of the current induced in the coil is as shown. Okay, so we have the current they are showing us is this one. Those arrows that you see, that's our current. These ones, not remember, current must flow in the coils, so these arrows are our current. Right, so if you take your hand using your right hand rule, right, you can take your hand and you will find that it will look something like this. You take your hand and you make sure your fingers are curling in the direction of current, and then you'll find that your thumb is doing the, so your fingers, you will see the nails, right, and then your thumb, you won't see the nails. So you will be staring at your fingers, so they are curling out of the page, right, and then the thumb is pointing that way. And remember what we said, the thumb always points in the direction of what? You can pause and try to remember. Yes, so the thumb always points in the direction of the North Pole, right? Because what essentially happens, once you start running current in a solenoid, you get a magnet. The solenoid becomes a magnet, right? So yeah, that's just us interpreting the question. But the North Pole of the solenoid can also be affected by this guy, the magnet, and the movement of the magnet. So yeah, for now let's leave it there. But if you're using the right hand rule, just know that the North Pole of the magnet will be this side and the South Pole will have to be this side as a result. But remember what we said, the North and the South Pole, or the polarity of a solenoid, changes. It changes. It's not fixed. It's not constant. It's not like a bar magnet. You see, with a bar magnet, if this is a north and this is a south, it's always like that. You can't change it. You would have to physically break the magnet or whatever, but you can't change it. But with a solenoid, it changes almost all the time. You reverse the direction of the current, it can change. You change the direction of movement of the bar magnets, this one, it can change. So what I mean by reversing the direction of the bar magnets, I mean if you're essentially taking the magnet that way, you change and you're now taking the magnet out instead of in. Okay, so it changes all the time, or almost all the time. All right, so that's the idea I want to drive, or the point I want you to get. So now we have question or I can write it this side. 2.1 states Faraday's law of electromagnetic induction in words. Right, so remember, with electromagnetic induction, what happens is we just have a changing magnetic flux, and then it induces an EMF, and then now the magnitude of that induced EMF is dependent on how fast this magnetic flux is changing. So what essentially we end up saying is the magnitude of the induced EMF, okay, let's write this, is directly proportional to the rate of change of the magnetic flux. So unlike your Newton's second law and the Newton's universal law of gravitation and so on, you don't have inversely proportional. You don't have that phrase in this law. This law just talks about direct proportionality between the induced EMF and the rate of change of the magnetic flux. So it's the shortest one so far. Right, so yes, we write that. So what happens is, before an exam, you must always make sure you know all your laws and your definitions, because they count a significant portion of your exam. Okay, so this is how we state the law. The magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux. So you'd have EMF is right. So that's the law of that's Faraday's law of electromagnetic induction, but stated in formula form. So it would look like that in formula form, but in words, it's what we've stated here. So when they say the rate of change of the magnetic flux, they are referring to this portion of the formula, this whole portion. Remember, rate, it's usually any parameter divided by time in a formula. So that means a rate or change per unit time. Depends on how you define it. So now this is what that would look like. So let's go to 2.2. Here's 2.2. Yes. So we are asked to determine the polarity of the bar magnet at X. Choose from North Pole or South Pole. Okay. All right. So remember what we said. Our thumb is always pointing to the north pole of the coil. So we will have a north pole here, right? And then now, to answer this question, 2.2, we are asked to determine the polarity of the bar magnet at X. All right, so if you remember, once you involve a bar magnet and a solenoid, you will use the right-hand rule, Faraday's law of electromagnetic induction, and also Lenz's law, right? So Lenz's law says, since this current that we see here is induced as a result of this magnet, right, passing through the solenoid, then remember, if this is the north pole of our magnet, it means this magnet that's coming in, because at this stage, at this part of the process, the bar magnet is going inside, right? So as the bar magnet moves inside, it induces an EMF in the solenoid. So that induced EMF will then produce a magnetic field that must repel the bar magnet. So for it to do that, it must build a pole here such that that pole will face the pole of the magnet, it means it will sort of copy whatever pole is at X, right? So that you get a repulsion, because remember, for magnets to repel, they must be like poles. So it means if this one is a north, there must be a north at X as well, so that these two can repel. So that's what essentially happens according to Lenz's law. So the magnetic flux, right, or the change in magnetic flux rather, that the magnet provides to the solenoid, right, what happens is that change will induce an EMF inside the solenoid and ultimately a current, and then that current will then now induce a magnetic field that will oppose, that will have a polarity that will oppose the bar magnet. Always, it always aims to do the opposite of what the bar magnet is doing. So if the bar magnet wants to go inside the solenoid will want to kick it out. So for it to kick it out, it must have a polarity at the entrance here that will allow these two magnets to repel. By two magnets, I mean the bar magnets and our solenoid, because remember, once we have current running in the solenoid, it then becomes a magnet itself. So that's why this X will be a north pole. So we can comfortably say X is a north pole, right? So just for your own curiosity, perhaps look what would happen if instead of having a galvanometer here, I put a power source, and then the current is moving in a certain direction, right? What will happen now to the polarity of the solenoid? And if I come and bring a magnet too, is it physically possible? And so on. What would happen? Just go and look, just out of curiosity. That's something for you to look into. All right, so now, yes, that's our answer for 2.2, north pole. So we can write that there, north pole. Right, as already stated, we just used Lenz's law. So because remember, the current inside the solenoid is there because of the movement of the magnets in and out of the solenoid. So then that's how the poles develop. So that's how we are sure that this has to be a north pole. It means now the magnet has a north pole here at X and the south pole here at that unnamed section. But yeah, so that's how the magnet looks like currently. So we know that this is just a north and this is a south. But for the solenoid, it's not fixed. It changes all the time. The polarity of the solenoid changes all the time, especially if you have the magnet moving in and out, in and out. Okay, so let's go to 2.3. 2.3, they are asking us, or we are being asked, what is the polarity of the coil at Y? Right? As the bar magnet exits the coil, choose from north pole or south pole. We apply the very same principle now. We say, so what we say is, if the magnet is moving away from the coil, right? So it will create, right, the induced EMF and ultimately the current inside the coil or solenoid will create a field such that it will want to oppose this change. So what does that mean in simple terms? It means as I pull the magnet away from the coil, the coil or the solenoid wants to pull the magnet back inside. So magnet, I'm moving it away from the solenoid. Solenoid says, no, 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 I want my magnet back. Solenoid tries to pull it back. So now then the question becomes, how do you make sure that, because this is our power magnet, right? And it has N and it has S. And then this is our solenoid. Let me use a different color for our solenoid. Let's say our solenoid is this purple here. It also has poles, right? But we are mostly interested in the poles at the ends of the solenoid, right? Because they change. So if I'm on this side of the solenoid, I only care about this side. I don't look at that side, right? Because something different is happening on both sides. So now I'm looking at this side specifically, the left, not the right of the solenoid. Okay, so I'm saying I'm moving the magnet away from the solenoid, and the solenoid is trying to attract it back. Remember, the solenoid is also a magnet. So how do you make sure magnets are attracting each other? You create unlike poles. So what that means is the poles that are facing each other must not be the same. So it means the pole of the solenoid that's facing the pole of the magnet, those two cannot be the same. So if this is south pole, it means my solenoid at Y must be north pole. Then attraction will occur. Okay, so that's how it works. That's what happens. So if you check, if you said this was N initially, right, and therefore this is S, it would limit you. Now you would think, if this is both S, then Lenz's law doesn't hold. But that's not how it works. It always changes. Okay, so at this point, this is our N, right? It means this side will be our S. But when the magnet was still moving inside the coil, this was our N, north pole, and this was our S, south pole, right? So when magnet is moving inside, this is our north, that's our south. When magnet is now moving out, this becomes our north, and that becomes our south. So you see, it flips. Right, so those are two separate situations, and they result in two separate different polarities. It's like the polarity is rearranged in a sense. All right, so that is how you would logically justify what happens there in the solenoid. So we would still have a north pole here. Okay, so yes, this one was a short question. This brings us to the end of our question. Thank you very much. I will catch you on our next video.